Hello folks, Professor Fiore here, and welcome to part 2 of our 4-part series talking about the Pocket Rockit personal amplifier. In part 1, we talked about the general overview of the circuit, gave you some idea of what it can do, how it works, and the sort of big picture approach to it. Right? So this is a little amplifier, small physically. You can plug your guitar, bass, electronic keyboard into it, plug some headphones into it, or maybe some small loudspeaker, and you can practice. Right? It's nice. Put the headphones on. Don't bother people. Right? Very convenient little thing. You can take it with you. Throw it in your guitar case, and off you go. So it has built-in distortion. It has 3-band EQ, a few other little tricks thrown in there. Okay, so we're just going to look in this video on the front end, which is basically the preamp distortion part. And then in part 3, we're going to look at the EQ section. And part 4 is going to zero in on the final section, which is the power section, the thing that drives your headphones. All right. Okay, so overview of the first stage. First thing to say is this circuit needs a high input impedance. Why? Because we're assuming you're going to plug in a passive bass guitar or electric guitar, and that demands a high input impedance. You can't use a typical, say, 10K or 20K input impedance you would find on the auxiliary input of your stereo, right? Your stereo amplifier. That's not going to work quite well. You might have tried this, get a little adapter, plug your guitar in there. It doesn't sound quite right, and there's good reasons for that. One of them is the impedance mismatch. So this circuit does have a relatively high input impedance. It's about 500 k ohms, about half a megohm. So certainly good enough for passive guitar or bass. It has a variable high gain section in this preamp, which we will use for overdrive, in other words, to create distortion. And this is kind of a softened sort of distortion. I'll show you how you can modify it, for taste, so you can monkey with some of the values here. And that's really, I think, an important thing, is you breadboard this thing and plug your instrument into it, play it, and then twiddle with the values a little bit until you get what you like. Okay, this happens to work out to what I liked. That's not necessarily what you like. All right. It does have a fairly low extended frequency response. So this thing will go down to like 20 hertz within like a dB or two. Why? Well, maybe you have a 5-string bass. You got a low B. Okay, so that's going down, 30 hertz-ish. So we want to keep that flat. Or maybe you're using like a Chapman stick or something like that. So again, you got that low string. You want to get a nice super flat response down there. So this will do that. It is set up for single supply biasing, and that's going to require some extra circuitry, but that's really a result of the fact that we're going to run this on just one 9-volt battery. If you were really gung-ho on this, you could redesign it, actually remove a whole bunch of components, and use 2 9-volt batteries. But my goal in doing this was to, keep it small and simple. And quite honestly, the extra circuitry, the extra components needed take up less volume than a second 9-volt battery. So that's the way I did it. That's why I did it that way. All right. So as I said, it does have kind of a soft clipping, and I'll explain how this works and how you can modify it. You will probably be interested in some other related videos, right? If you haven't already watched them, or you're kind of new to the whole operational amplifier thing, you probably want to take a look at the non-inverting amplifier video that I have, the video on single supply biasing, and more direct to the point, there's another video called Guitar Fuzz, which basically talks about how you can create fuzz, right? Distortion. You want some distortion. So those are 3 good videos to look at. All right. Okay, so recap. Here's the circuit we're looking at. 3 sections. Here's the front end. This is what we're going to look at today in this video. The middle section, this will be in part 3. This is the EQ section. And finally, part 4, right here, this is the power output section. All right, so we're going to focus on this section right here. So slightly redrawn in Tina, here's that same circuit. All right, that same part. So here comes your instrument over here, and then this EQ section, right, would be sitting out here somewhere. So we're just going to tap off there. What's going on here? Well, the first thing I'm going to say is note this is running on a single polarity power supply. So the negative power supply is going to ground, positive power supply is going up back over here to a 9-volt battery. And if you remember in the first video, I explained why D1 is here. D1 is here in case you accidentally put the battery on backwards. You would have a negative voltage and you'd blow up your op amp in a blink of an eye. All right, so that's why that diode is here. But because we have a single polarity power supply, we have to bias the op amp at a midpoint. In other words, roughly 4.5 volts, or once you subtract off the diode drop, maybe more like, 4.2 volts, but whatever. We need to do that, and we also need to make sure that the DC gain of the amplifier is 1. Okay. Finally, we want to block the DC voltage from going back to the source as well as out to the next stage. All right, so we need coupling capacitors. That's why there's so many capacitors in here. Most of these are like blocking and power supply associated kinds of capacitors. Okay, let's get rid of one really quick, and that's this C4 over here, this 1.5 micro. That's power supply, sort of a filtering thing. This is very common. When we do ICs like this, we put somewhere around a 1 microfarad cap, like right on the power supply pin. Make sure that power supply pin is a good AC ground. So we have a cap there. All right. Now this pair of 220Ks, R2 and R3, are set up, right, equal voltage divider. That's set up to get the bias that we need. In other words, that, ideally half of this power supply over here. Okay. So like I said, a little over 4 volts is going to be at this point. And this is going to be fed into the plus input of the op amp. Now, what's with all of these other things? Like, what the heck is R4 and C2? Well, again, if you look back in some of the preceding videos, I explain how you can decouple the noise that might exist on the power supply, because you might have like a cheap 9-volt wall wart, battery eliminator over here, kind of noisy. So you want to get that noise out of there. You don't want to couple that directly into the input of the amplifier. In other words, if you just took this 220 and this 220 and you just tied them right to the input line, whatever the noise was coming in, it's going to go right in the op amp. Don't want that. So this creates a little sort of frequency selective kind of network, because C2 will basically short this node to ground. So now you've got a big loss for the noise signal coming in here. It's going to have a big divider on R2. So this will be a low impedance because of C2. All right. Now, if you just left it like that, you'd also have a low input impedance. So we need something from this point in, which that's what R4 is for, the 470K. Essentially, this sets the input impedance, because this will be a decent AC ground, right? This will be a low impedance point. So coming in, basically to ground outside the op amp, you see this 470K. So you got about a half a meg for an input impedance, and that'll be great for, a passive guitar pickup or bass pickup. To eliminate the DC voltage from going back to the instrument, we have C1 over here, and this is set up 100 nanofarads. This will give you a very low break frequency. This will create a lead network with the input impedance. And when you calculate that out, you're going to see that's well below the human audio range, right? Young, healthy humans, good hearing, lower limit, 20 hertz or thereabouts. Okay. All right, so what's R1 and C3? Well, this creates a little lag network, and this will remove a lot of high frequency like radio interference. Okay, but again, that's above the audio range. So that's, again, just sort of a cleanup kind of thing that's there. All right, 68 picofarads is not much. So now we move along to the op amp itself, right? So all of this here is just to make that bias and to get rid of any potential noise that's on the power supply line. Okay. Okay, so that's coming into the plus input, and then out here we have some resistors and a cap. So you can notice, hopefully, that this is a non-inverting, a series parallel feedback arrangement. C5 is here to guarantee that the DC gain is unity because, whatever this DC voltage coming in is, that's what I want coming out, right? If I didn't have this cap here, whatever the gain is, it's going to try to multiply this input DC by that gain, and we're going to have a huge DC output here, which most likely would create saturation, right? Destroy our musical signal. So C5 basically opens up, which means that your Ri, which would be this combination, would be infinity. And whatever you have over here divided by infinity, right, that's going to be pretty close to 0, plus 1, right, because your gain is going to be Rf over Ri, that quantity plus 1. So your gain will fall to 1, right? For DC, that's what's going to end up happening. But for the audio range, the gain is going to be whatever the pot is set for divided by R6, this 1K, plus 1. So if you brought the pot all the way over, right, this is wired as a rheostat. So if you brought this all the way over, you'd have 0 ohms, and you'd have 0 over 1K plus 1, which would give you a gain of 1. On the other hand, if you brought it the other way to the other extreme, you'd have 100K over 1K, which would be gain of 100 plus 1, or 101. So you got a gain of roughly 40 dB in that case, right? So this thing goes from anywhere from basically 0 dB up to about 40 dB, pretty wide swing, okay? And out here, your signal is tens, maybe hundreds of millivolts, all depending on, what the instrument is that you're actually driving. So clearly with a gain of, 50 or 100 or something like that, you can overdrive this mightily. C6 is here to prevent the DC from getting to the next stage. And here is this fun little bit of resistors and diodes. So this is here to create some clipping. Now, in most fuzz boxes, you would just see a pair of diodes like this sitting at the output. You wouldn't see R7 and R8. They wouldn't be here. You would just have the signal come out, have these diodes clip, and that would be the end of it. Okay? So you crank the gain up over here with this pot, P1. The more gain you get, the more clipping you're going to get. All right? The more fuzz you have in your signal. So what R7 and R8 do is they tend to sort of buffer and soften the abrupt clipping of these diodes, right? Positive or negative polarity is going to clip at 0.7 on these. But now you actually have this extra resistive combo, which can also have a little bit of a voltage drop across it. So you're going to see that we have a little bit of sort of rounding rather than these really abrupt kind of curves. Now, if you want to kind of play with this, if you want a softer kind of transition into fuzz, just make these resistors a little bigger. If you're going to monkey with these, actually when you breadboard it, you could just put a little pot in here, like a 1K pot, 500 ohm pot for the two of them, and just sort of, monkey around with those and see what you like. But, if you're going to pop out some resistors, just start changing them by like a factor of 2. So, these are 68s. Okay, try a pair of 150s. Try a pair of 330s. Okay, maybe, you might go up to a K. I don't know. You just listen to it. Play and listen, play and listen, play and listen. All right, see what you like. Okay, so then at this point, you just tap this off and we go to the EQ section, and that, of course, will be in part 3 video. So let's take a look at what this thing is actually doing. Before I forget, let me check the setting on here. Okay, so we're only at 10%. All right, for the pot setting. So we only have 10K here. So we're getting some gain, but not tons of gain. Okay, we're getting a little bit of gain. So maybe the first thing we'll do is we can check the AC transfer characteristic. In other words, check the Bode plot. Because I do want to make sure that it's going, full spectrum. Okay, so as I said, that's a gain of about 10, because we had 10% of 100K, which is 10K. So that's 10K over 1K plus 1, gain of 11. So a little over 20 in decibels. And we can see, yeah, this is nice and flat. Here's 100 hertz, 10 hertz way down here. This is only down, at 10 hertz, it's not even down a full 3 dB from the looks of it. And then up here, this is extending out to like 100K before it's even starting to drop about a dB. So really nice. Of course, as we crank up the pot, this is going to shrink down. But I'll tell you right now, with a gain of 10, if we're at 100 kilohertz, when we crank this thing all the way up, we'll still be up to the upper limit of human hearing. All right, it'll crank down a little bit. We're not really going to see any change down here at the bottom end, but still we're going to get the full band for the the spectrum of the instrument in question. All right. Okay, so let's do a little bit of transient analysis on here. Okay, so like I said, we only have 10%. Now, if you look carefully, you might notice that this is the output signal, right? This maroon. This, as expected, it's in phase, and we are seeing gains, so that's that's wonderful. But it is, if you look closely, maybe not a perfect sine wave. You look at the top of this, it looks a little weird. It looks a little slightly asymmetrical and a little like squishy. If you're used to looking at sine waves all day, okay, you might notice that. It's kind of subtle. It's, I don't know, maybe 5 or 10% THD, I'm going to guess, because it's not a lot, all right? But you would hear it, sustain a note. You'll hear a subtle change there, okay? Well, let's go back and crank the pot up a little bit, all right? So maybe we'll change this to like 20%, okay? We'll see what's going to happen. By the way, before I go into this, notice here's the 1 volt, right? So, that 7/10 is around here. So we're just starting to get a little nonlinearity due to the diodes. Okay, now we can definitely see there's some flat topping going on here. But I also want you to notice that there's a little break point, right? You can see it right here. And that's because of the additional resistors that's doing that. So this is, not really squaring it really hard like if you just had straight diodes there and that was the end of it. Okay, so you are seeing a little bit of this softening. But again, I have to reiterate, this is a matter of taste on how you want this thing to sound. So you can, play around with these. All right, so let's let's crank this all the way up, and you can see that this thing can really go into some severe overdrive. I mean, if you really want that dulcet metal tone, you can get it. And there you go. So you put your sine wave in, and you're getting pretty much a square wave out, right? So you can really get that, metallic overdrive sound, all right? Now, as long as we got the pot cranked up, let's go back and check on the Bode plot. All right, so like I said, big crank and gain here, 40 dB. Each one of these little clicks here is like a dB, so you can see down here at 10 hertz, we're only down about 2 dB. And then on the high end, there's 10 kilohertz, here's 20 kilohertz. So even at 20 kilohertz, we're only down 2 dB. So you're never really going to hear that at 20 kilohertz. So we know that the amplifier is full flat response, and that's great, right? It's not changing the timbre, at least spectrally, right, of the instrument. Even if you had like a insanely high gain and the signal was so small that, it wasn't distorting, okay? That's important. It certainly has enough a low frequency end for any kind of bass instrument, okay? And now that we have that, now that we know that we can get this huge signal and so forth, which will distort nicely over here, now we can run that into the EQ section. This hasn't modified the response of the instrument other than distorting it, right? And now that'll be up to the EQ section to modify. So you want to have, generally speaking, you want to have the distortion first and then the EQ so that you can alter the basically the amount of distortion, how it kind of sounds. Because if you EQ it first and then you do the distortion, that is going to kind of unbalance the original EQ that you put in, right? You put a lot of bass in, you're going to have a really big signal, and a lot of the distortion you're going to get is because of the boost in the bass. So, you wouldn't have any way of sort of turning down something that was just a little too edgy sounding. By having the EQ second, you can do that, right? You can get a lot of this and then, a lot of distortion and then turn down the treble a little bit to kind of soften the edge of it, right? So typically we put the EQ section second. I'm not going to talk about the EQ section because we've got a whole nother video for that, right? Great. Okay, so stay tuned. Part 3 will be coming up. If you have any questions on this front end, you know what to do. Put them down in the comments. Until the third part, this is Professor Fiore saying, have a good one.